When solid magnesium metal reacts with strong hydrochloric acid, the metal rapidly breaks down and forcefully releases hydrogen gas. Our goal is to capture that gas, measure its physical volume, and use that data to calculate exactly how many liters of dry hydrogen are produced per mole of magnesium at standard temperature and pressure. Because we are working with 6 molar hydrochloric acid, a highly corrosive substance, you will need to wear your safety goggles, gloves, and a lab coat for the entire procedure. Capturing a gas over water presents specific physical challenges. However, working through this collection method provides the exact measurements required to translate a physical-chemical reaction into precise molar calculations. Step 1 is defining our starting material. Cut down a piece of magnesium ribbon to approximately 5 centimeters in length and carefully weigh it on an analytical balance to determine its exact mass. Next, take a length of fine copper wire and wind it around the magnesium strip to encase it completely. Make sure to leave a long section of wire extending from the top to act as a handle. As shown in this close-up illustration, the copper wire cage must tightly wrap the magnesium with 0 gaps. If the cage is too loose, unreacted fragments of the metal will slip out, float to the top of the tube, and ruin the experiment. By perfectly securing the metal, we ensure that the entire sample reacts. This exact, fully reacted starting mass acts as the physical anchor point for every molar calculation you will perform later. Secure a clean burette in a clamp. Check that the bottom stopcock is completely closed, and tilt the glass slightly. Pour in 10 milliliters of 6 molar hydrochloric acid. With the burette still tilted, slowly trickle tap water down the inside of the glass to fill the rest of the tube to the brim. This cross-section diagram illustrates why you must pour so gently. The denser hydrochloric acid sits undisturbed at the bottom, while the lighter water layers on top. Pouring too quickly will agitate the heavy acid, initiating a premature reaction. Once filled, gently tap the side of the glass to dislodge any microscopic air bubbles clinging to the inner walls. Successfully stratifying these two liquids creates a physical time delay. This buffer gives you the crucial seconds needed to properly seal the system before the acid ever touches the metal. Holding your copper handle, lower the magnesium cage about 3 centimeters into the water layer. Hook the wire over the glass edge and seal the opening with a 1-hole rubber stopper. The stopper should displace a small amount of water to prove there is absolutely no air trapped inside. Cover the hole in the stopper tightly with your finger. Quickly invert the entire burette into a beaker filled with water and clamp it into a vertical position. In this macro footage, gravity takes over. The denser hydrochloric acid physically falls down through the lighter water column, pooling at the bottom until it violently collides with the trapped magnesium. The reaction will rapidly produce hydrogen gas, pushing the liquid level down. Once all bubbling has ceased, wait a full 5 minutes. This allows the newly generated hot gas to cool down to room temperature. Ensuring a perfectly sealed, zero-air environment before triggering the reaction guarantees that 100% of the volume you capture is pure evolved gas from the magnesium. With the hole covered by your finger once again, transfer the inverted burette into a large water cylinder. This diagram shows equalization. Manually align the internal liquid meniscus with the water level outside. To read the inverted burette, subtract the visible meniscus line from 50.00 milliliters, then add the uncalibrated volume, the empty space between the 50 milliliter mark and the stopcock. To find this hidden value, flip the burette right side up, fill it exactly to the 50 milliliter mark, and physically drain only that uncalibrated section into a 10 milliliter graduated cylinder to measure it. By perfectly matching the internal and external water levels earlier, you prove that the trapped gas pressure exactly equals the room's barometric pressure. This equalization makes standard gas laws applicable to your volume reading. Before dismantling your station, record 3 essential environmental factors: the temperature of the room, the temperature of the water bath, and the current barometric pressure. Because you collected the gas over a water column, the captured volume in your tube is actually a mixture of 2 things: hydrogen gas and water vapor. To account for this, use your recorded water temperature and a standard reference table to find the specific vapor pressure of water for today's conditions. This formula shows how we isolate the dry hydrogen. The partial pressure of your hydrogen gas equals the total room pressure minus the water vapor pressure. Failing to mathematically subtract this water vapor component would artificially inflate your pressure readings, leading to highly inaccurate density calculations later on. This data table highlights the complete checklist of variables you must log before leaving your station: the exact mass of the magnesium, the volume of gas collected, the specific temperatures, the barometric pressure, and the calculated vapor pressure. To verify the precision of your technique, set up and run a second trial. Your goal is to achieve results that fall within a 5% margin of error of your first run. When you are finished, safely dispose of the neutralized acidic solution down the sink with plenty of running water and thoroughly clean all your glassware. For your post-lab work, you will take these raw variables and apply the combined gas law or the ideal gas law. This will convert your capture data into the precise volume of dry hydrogen at standard temperature and pressure. Mastering this highly controlled physical procedure allows you to bridge the gap between theoretical stoichiometry written on paper and the real-world elemental properties of gases.